Hello, my name is Keirnan LaMarche, and I lead product development for continuous manufacturing at Patheon, now part of Thermo Fisher. I want to talk today about dynamic real-time models and their use as part of a control strategy for OSD manufacture. So let's first introduce the topics for this talk. First, I'll discuss process models and how they're related to residence time distribution. We'd like to also discuss real-time modeling. The term real-time describes how a model is implemented. Real-time model takes in live data and outputs predictions in time. Dynamic models are like other mass balance models commonly used in continuous manufacturing. However, the dynamic models' steady state conditions are not assumed. We'll discuss both aspects of the models we're currently using in our system and take a look at some general examples. Here at Thermo Fisher, we developed a flexible, modular, continuous manufacturing system with both a direct blend compaction and direct blend encapsulation options. As it turns out, encapsulation has several challenges that are not present for tablet compaction, especially around process stops and slowdowns due to capsule handling issues. I'll discuss some of the ways dynamic modeling can work well with this type of process. We'll then look at some of the details around building and using dynamic models, and specifically we'll look at dynamic plug flow reactors, as these can be extra challenging. So why use models in a continuous manufacturing control system? Models play a very important role in continuous manufacturing systems where controlling the concentration of API and other constituents in the final product is extremely important. One of the benefits of continuous manufacturing is there are several ways to access data about the concentration, and with that information, control the product quality. For example, spectroscopic PAT methods can be used to predict concentrations at a point in the process using sensor probes and chemometric models. Or feeder data can be monitored and compared with RTD information about the system. And of course, real-time models can be used with feeder data to directly predict the product stream concentration. One important aspect about these systems is that RTDs themselves are a form of model. They are a representation of the continuous system and its behavior, and the residence time distributions are mass balance models. And they are, of course, critical for characterizing continuous systems properties. An RTD is defined at steady state conditions. Changes in the mass held within the system or the throughput of the material through the system will change the RTD. Process models, as we use the term here, are more general. In this case, a mass balance model is used to predict product concentrations directly without first calculating an RTD. Before we continue, here we see a picture of our feeder and blender system at Thermo Fisher. Our unit uses feeders, which can either feed a mill and then a blender, or directly feed the blender. And below this blender is either the encapsulator or tablet press. So when we say a model is real time, we're really talking about how the model is implemented, not what type of model it is. In the case of a process model or dynamic process model, that implementation allows predictions to be generated based on live readings of feed rate data that are constantly being delivered from the loss and wait feeders. The model combines the data with streams from other feeders and other units to make an assessment of the quality of the product stream on a second-by-second basis. This is using data and the model as a P&T instrument. An example shown here, you can see an upset in feed rate from one of the feeders, and this information travels through the model and results in a prediction of the concentration shift for this material. So the real-time predictions can work with either steady state or dynamic models. Residence time distribution, or RTD, depends on the state of the system. If the throughput changes, the rate at which the material passes through the system changes, which then changes the distribution of times a particle will be expected to leave the system. As you can see in this graph here, as the throughput increases, the material passes through the system faster. In addition, the width of the residence time distribution decreases. So at faster throughputs for a given holdup, you get less mixing. The material spends less time in the system, and there's less distribution of particles throughout the system that can cause that mixing to occur. Obviously, the goal of operating a continuous manufacturing system is to remain as close to steady state as possible, but in some conditions, this can be difficult to achieve. Deviations can occur, process stops can interrupt production, some of those process stops can require the equipment to come to a stop and then begin again. And as we'll see, some pieces of equipment are more prone to these interruptions than others. And of course, process startup and shutdown are also dynamic times for a process. In other conditions where you might want to use dynamic models, let's say you have a product with multiple strengths, it may be most efficient to manufacture those at the maximum throughput possible for each strength. In that case, a single dynamic model, which is capable of incorporating throughput changes in its predictions, can be an effective, efficient solutions to all of these cases. So let's see an example here. This is a real-time example of the real-time process model. This is a model of our direct blend encapsulation system. We are using simulated feeder data here for the feeder inputs. What's shown is the total mass throughput of the system, which is just the sum of all the feeders and the feed rates. The API feeders, feed rate, and the process model prediction of the system output concentration are also shown here. The calculation is carried out in real time, or can be carried out in real time. Data from the feeders is input to the model, and API concentration is the output. So you can see here an example of the process model response to a step change in API concentration. When the API concentration shifted, the concentration of the output also started to shift. Note that the total throughput remains constant in this example. So let's look at a slightly different example. This is the same step change simulation as the last slide, only now a change in throughput is also included. You can see the rate of the change in the concentration adjusts when the change in throughput occurs. So this is how our model can take this sort of thing into effect. As the change in throughput occurs, this changes the rate at which the mixing occurs and how the process reacts in time. In addition to changes in throughput, changes in holdup have a similar effect on concentration behavior, and these changes can be simulated with an appropriate dynamic model. So ultimately, the goal of a real-time process model in a control system is to determine the product stream should be accepted or rejected. This is another example looking at a simulated feeder upset. The red dashed lines here represent the rejection limits. After the feeder was upset, the concentration is predicted, and when that predicted concentration exceeds the limit, the product stream can be automatically rejected. After the product concentration prediction re-enters the limits, the stream can be accepted again. So when we started looking to do dynamic process models for real-time predictions, it was in response to some of the unique challenges we were facing when working with the continuous manufacturing of encapsulated products. Our system uses a large encapsulator, the MG2 Planeta 200. This can produce up to 200,000 caps per hour. For a direct blend system, with the throughput range we typically use, it has a fairly large holdup of 4 to 7 kilograms. This results in a great deal of mixing and relatively slow dynamics. So the mean residence time can be about 20 minutes. The encapsulation process requires empty capsule shells to be fed to the machine. Each capsule opened, then filled with a powder slug, and then closed again before exiting the machine. If the empty capsules are damaged or mishandled by the machine, the process can slow itself down and try to remove stuck capsules. If that's not possible, the process has to come to a stop, and that be the stuck capsules manually removed. This makes encapsulation more dynamic than most tablet press operations. These issues can arise anywhere from about once an hour to once every few minutes if the capsule quality is especially bad. So unpredictable changes in the encapsulation throughput and frequent process stops leads to holdup changes in the encapsulator. Basically, as you change your encapsulation rate, your feeders are going the same speed, and this leads to a buildup of material inside the encapsulator. And to remove that material, you then have to speed your encapsulator up. So this is a challenge for control with real-time steady-state models. So what we did is we started looking into dynamic models which can take process speed changes and these holdup changes into account as a potentially efficient solution for this situation. So to build this model, we went through a particular process. First, we defined some important goals. We wanted an accurate model that also represent the physical structure of our continuous manufacturing line. This meant we wanted to include each unit operation in the model, including the co-mill, the blender, and the encapsulator itself as separate units that we could model separately. For the model data inputs, we wanted the mass rate from each feeder along with the level data from the encapsulator. Building the model followed 4 steps. The equipment was assessed to determine probable model structures. A set of CSDRs were selected for each unit, along with a single plug flow reactor. Data was collected from the system and analyzed analyzed. So we look at the behavior of the system and finalize the model structure. And then this data was used to calibrate the model. This model ended up having only 2 fit parameters. And after that, the model performance was checked against a separately collected data set. So let's take a look at that data set here. So here's the process model. It's being compared to the data set that was selected collected for checking the model. The model was calibrated against a different data set, which was collected about 6 months before the trial shown here. The experiment used acetaminophen and was carried out with large step changes in API concentration. The goal here was to challenge the model with a wide range of blend properties and rapid large changes in concentration. The concentration set points were varied between 14 and 42 weight percent, and the system was also subjected to large variations of throughput from 21 to 32 kilograms an hour. The API concentration was monitored with an NAR model, and the probe was placed in the dosager bowl and encapsulator. As you can see, the model adequately represented the concentration as determined by the NAR probe. This is despite large concentration shifts and therefore density shifts in the blend, as well as sudden changes in throughput. In the throughput process data, you can see process interruptions, which occurred when the encapsulator was forced to stop due to capsule handling issues. Despite these process stops, the model was able to perform accurately. So with one model, we can simulate a wide range of process contingents, both concentration differences, process throughput differences, and this is a model with only 2 fit parameters. So this is a very efficient solution for what we're looking for, both looking at wide ranges of material properties as well as wide ranges of throughputs, and a dynamically changing encapsulator when we wanted to manufacture capsules. So let's take a little bit and look at how these dynamic models are built. All the models are built in the same way as steady-state models, from a mass balance of the system. However, in this case, the assumption of steady state is not applied. The mass balance is used to generate a series of equations, which can then be solved to determine the concentration of the materials in the system over time. For CSTR models, the equations form a series of ODEs, which can then be solved using normal methods, for example, Runge-Kutta. An important aspect of this solution is that they can require additional data to complete the mass balance in these model equations. This data can be mass holdup. It can come from level data from a holdup area in the system, or it can be from measurements of the exit rate, the output throughput of the system. This is just to close the mass balance when you have a dynamic system. Now, plug flow reactors are a bit more complex. So for a plug flow reactor, the solution to the mass balance is trivial when the process is at steady state. The plug flow reactor simply acts as a delay. Information about the concentration takes a defined time to pass through, but is otherwise unchanged. When the plug flow reactor faces changes in throughput or holdup, dynamic changes in delay time for the data occur, and this can lead to compression or lengthening of waveforms. In theory, it shouldn't cause mixing, but you have material that's moving in and then moving out at different rates, and therefore being compressed together or separated during that process. So the dynamic form of the mass balance for a plug flow reactor is a partial differential equation. This defines the concentration as a function of both time and position within the plug flow reactor. The PDE can be solved by discretization and tracking materials that passes through the plug flow reactor. This is not especially difficult. It's only a 1D discretization. It does mean that we're now modeling the interactions within the plug flow reactor itself with some fairly safe assumptions. This is not very difficult to do, but it is more computationally and memory intensive than an ODE solution. And this is important when you look at a real-time solution, as you want that solution to complete in a relatively short period of time so that you can have a real-time prediction that doesn't fall behind reality. So to conclude, real-time prediction generated from mass balance-based process models are an efficient solution to the control of product streams in the CM system. Dynamic models also offer benefits. They can handle a wider range of throughputs and even mass changes in holdups in systems, and then models or residence time distribution methods based on steady state behavior alone. Process upsets, process stops and starts, or more complex equipment, for example, encapsulators, can be more accurately represented with dynamic models. These models have been developed and are used in both our direct blend encapsulation and direct blend compaction line. So I'd like to thank all of my colleagues at Thermo Fisher, and I'd like to thank you for listening. If you're part of the live presentation, I'll be available for questions. Thank you.